Hey everyone, this is the second part of the lenses and optical instruments discussion. So we left off talking about converging lenses, and as I said, we're going to kind of do a few more practice problems with this before I kind of mention a few other things with lenses. This one shouldn't be as long as the other one. So here even though it says that it wants you to sketch the diagram as the final product, I actually recommend you do it in the beginning. But pause the video, work on this yourself, and we'll go over it in a second. All right. So the main thing that you have to be aware of is making sure that your placement for the focal points and the lenses makes sense. Unlike last time where I just kind of threw things together and just roughly guesstimated, it wouldn't work the same way here because if you look here, the converging lens has a focal length of 20 centimeters, the diverging is 10 centimeters, and they're 25 centimeters apart. So what that means is they're going to be overlapping each other. This is what my diagram kind of looks like. So here I have my converging lens, I have focal point 1 over here and here, I have my diverging lens with the focal point here and here. So you'll see how they're overlapping like this. I do also want to be a little bit consistent with where I place my object. So it's about 3 times as far away from the lens as its focal point. So I'm just going to put the object right about here. That's about three times. That's as good as I'll be able to get. So first point goes parallel and then through F1. So most likely from here, we're going to end up creating our image most likely on this side. Well, we'll see. The next point is going to go through the center. And then the last point through the focal point. And then parallel. Alright, so right about here. This is where my object is going to be placed. Alright, so far everything kind of makes sense. Now from here, it's going to be a little bit messier doing the diverging lens. So remember the first line, I'll just do this one real quick. Oh, that's not lines. The first one that I'm going to do is a line through the center only because like I said, this one's always the easiest one to do. So a lot of times with these messier ones, I like to do them. And then I'm going to have a line that goes, it's also going to go parallel, but instead of going through the focal point like it would through the diverging lens, it's going to actually go through this focal point. All right. Remember, that's kind of like how it works. It's going to go like opposite it. And then where's the other one? The other one is going to go towards this focal point, and then it's going to go parallel. So it's going to kind of go along here, and then at this location, it's going to go this way. So what I have is that it's going to create an image right about here. I think that's where the 3 lines cross. So I'm getting an inverted image. Let's see if my placements actually were to scale and see what we get when we plug numbers in. All right. So first, what we have to do is use the equation once to figure out where the image is going to be formed. So when we use the lens equation and we plug in the numbers, we get that the image distance is 30 centimeters from the first lens. Now if I look at my diagram, that does kind of look about 30 centimeters. This focal distance was 20 centimeters. So yeah, I would say that that is about 30 centimeters away. So because of this, I know that the distance between these, I'm going to have to make sure that I take into account the spacing. If this is 30 centimeters away from the first lens and this is 25, then I know my spacing is going to be 5 centimeters to the next one. And I'm going to make sure it's negative because it's being formed on the right side of the diverging lens. Remember, our notation is that if it's on the left side where the light is coming from, that's when it's positive for object distances. So my object distance for the diverging lens is going to be negative 5 centimeters. Do the same thing, and I end up getting the image formed as a positive 10. So what that means, it's still going to be formed on the right side. Again, for images, positive means right side. So I do end up seeing that. I do have it created here. Um, Unfortunately, I have it that it's actually closer to it. So it looks like some of my placements might have been off with that. Um, that's too bad. But I do get that it's a positive 10 centimeters from diverging lens. Now for the magnification, again, we take the product of the two. When we plug these numbers in, we get -1, meaning that it ends up being inverted. So I do see the inversion here. Um, yeah, so I do end up seeing that. Um, I was trying to see if there was anything else. I don't get it that it's the same height, but uh, it could also be the fact that this was, again, not really super placed in the proper spot. Um, so this is actually what a ray diagram would look like. You'll notice they do add in this weird line. Again, that's just so that you end up getting a line that goes through the center. Um, Actually almost does kind of look like the diagram I had, just flipped. But here you see that you have the line that goes through the focal point and then parallel. It'll form the image here, and then when you do your rays, making sure to do your little back tracing, like parallel and then through this focal point outwards, and then through the center and all that, you end up getting this image formed. All right. Actually, I see what I did wrong. I had this line go through this point instead of going through that point. So that actually was my mistake. If I fixed this line, um, my other lines would have also worked. So um, that was my mistake of kind of messing up on the diverging. There's a little too many lines going on, and the inversion kind of made it a little bit weird. All right. But you definitely want to make sure that you practice your diverging lenses. Like I said, they are on the trickier side. Even I kind of get mixed up every now and then with them. And there is a chance that you might see them on the final exam, especially in a combination type setup. All right, so this one's pretty interesting. It's kind of a way that we can find the focal length of a lens. So, pause the video, work on this stuff, and we'll go over it in a second. So, what you end up doing is you take these two lenses. So, we have a converging and a diverging lens. You put them right next to each other, and you get light coming from an infinitely far away source. And you figure out where does the light end up converging. So, the combination ends up focusing light at this location right here. We know that the converging lens is going to actually form its image. Its focal point is right over here. So we can kind of do what we normally do, making sure that we can use this to figure out what the diverging lens's focal length is. So we start off with our equation. So we start off infinitely far away. So for the most part, not really going to worry too much about it. We know that the focal length of the second of the diverging lens is pretty much going to be the coming from this equation, which is our lens equation. Our object distance to the diverging lens is going to be the distance between the diverging lens and the focal length. So I can plug in FC for that. And I actually do know what the image distance is going to be. It's going to be where the final focal length is going to be. I apologize that there's so many focal lengths being thrown out there, but we end up getting that the inverse of the diverging lens's focal length is equal to the sum of the inverse converging focal length and the inverse total focal length. That's what this is going to end up being. We will have to make sure that this FC ends up being a negative because of where it's being placed. So you'll see here that even though the focal length for a converging lens is positive, because of our notation, since this image, quote unquote image, is formed on the right side of the diverging lens, then it's technically a negative object distance. So when we plug these numbers in, I get that the diverging lens's focal length is negative 36.5, which makes sense. Diverging lenses have a negative focal length, and that's what we get here. All right, and that's pretty much it. Now, I just want to throw in a little bit that we have an equation that's called the lensmaker equation, which is a much more in-depth version of the lens equation that we've been dealing with. If you notice, one of the things that I kept repeating is that these were thin lenses, and one thing that I didn't mention was how these sides are curved. I said that they're both, convex or they're both concave. However, I didn't mention if one was maybe more convex than the other or more concave than the other. I also didn't mention what type of materials this was made. So a lot of those will actually play a part in the actual setup. Now I'm not going to go into this derivation at all, really. This all comes from geometry, things of like using Snell's law for small angles and such. Like I said, taking advantage of small angle approximation and looking at geometries. What's the phrase? Similar triangles, things like that. And what you end up getting is this. So this one's a little bit more in depth of an equation to figure out what the focal length of an object is. So here we have an equation that deals with the index of refraction of what this material is. So depending on what glass, that could affect the focal length. But also now we have something that's going to deal with the radiuses. So for example, the reason why you might use this is depending on a person's eyesight or need for clarity, they might need different focal lengths for their eyes. So you can play around with what the type of material to get the focal length right, or you can even mess around with one of the radius of curvatures. So this is an equation that you could use to kind of make custom lenses to fit the focal length you need. All right. So here's just a quick question that you can try out. You don't have to. So if you want, you could pause the video. Otherwise, you could skip. But we'll go over it in a second. All right. So this is kind of what's called a convex meniscus, where you have a convex and a concave surface kind of next to each other. Even though they're both curved the same way, one is technically convex and the other one's concave by the way we're defining them. So they want us to know the focal length, so we're just going to use this equation. We know what the index of refraction for glasses, and they tell us the two radiuses. So we plug those numbers in. We're going to have to make one of those numbers negative because of the whole different type of surface. Um, like I said, how concave and convex are defined. And we get that the focal length is 87 centimeters. And then from there, we can use the lens equation, plug the numbers in, and get that the image is going to be formed 1.5 meters away from it. All right. Um, so cameras kind of play along with the concept of lenses. I'm not really going to mention a lot of this stuff. Um, so there is something that restricts how much light that actually reaches the film. And it's what's called an f-stop. And the f-stop is actually found by taking the focal length and dividing it by the diameter of this lens opening. So you have a lens, you have an opening amount that will actually allow only some light to come in, and it will strike a sensor on the other side. That's as far as I'm really going to go. Um, Now, I did want to point out this a little bit. So, as far as if you've ever seen one of these type of blurry images where you have one image that's very clear and one image that's blurry, a lot of ways they do this is by setting the focal length. So, for example, you can make it so that the image that's really far away, when it comes in, it gets focused at a point that's not at the film. So what it's going to end up happening is that it passes through and it ends up kind of making this what they call circle of confusion, and basically makes it very blurry, while the actual image that you're focusing on does get focused right at that at where the film is. Now there are ways, of course, as you know, you can take a photo of two objects that are two different distances and not get this. There's a way that cameras, take this into account. Again, I'm not really going to go into it because that kind of goes more into the engineering aspect. But a lot of times, what they could do is just have the lens vary its focal length for a bit and kind of combine all of it together. All right. I'm going to go through this one real quick, but as you know, the eye has a lens in it. That's how we see. So the way we're able to see different distances, you have the lens of the eye, and you have these muscles here on the other side, which will actually expand and contract it in order to change its effective focal length. So that's how we can kind of vary the distance that we can focus on. Um, the liquid kind of surrounding this does have a some almost like glass like index or refraction. Some other things that I want. Um, you end up having the image formed typically on the back of the eye over here. And on the back of the eye, you have two things. So you have rods and you have cones. So this is the retina, the back of the eye. Rods and cones, I can't remember which one does what, so I'm just going to guess on here, but one of them controls color. I'm going to say it's the rods control the color, and the cones control the amount of light coming towards the eye. So basically like brightness and darkness and color. Now, one of the interesting things, as a quick side note, is that the distribution of rods and cones is actually not consistent along the back of the eye. The edges over here and over here tend to have more light sensors. So I'll say that they're more cones over here, while in here it doesn't really have too many cones, but it has a lot more rods or color sensors. So what this ends up meaning is that When you're focused on an object, when there's an object right in front of you and you're focusing on it, the image is going to be formed right here in the middle. Uh, you're getting a lot of color differences, but the image is formed in the corners of your eyes, essentially the areas that you can see but you're not focused on, technically do not have any color in them. They're only black and white. Your brain a lot of times will actually fill in color. So you might be able to say, oh, well, I can see that there's a blue cup to the right of me. Well, it's because you already know that the cup is blue. So that's kind of why your brain fills that in. It says, oh, I know what this is. So it puts it in as blue. Also, your eye does kind of shift around, so it kind of does get a little bit of extra information. But for the most part, the light on the around the edges are technically black and white. This is actually one of the reasons why, if you've ever tried to search for something or look for something at night, when it's really, really dark, you never want to try to look directly at what you're trying to look for. You always kind of want to look to the side and look at things in the dark through the peripheral vision. So yeah, if you've ever wondered that, like, you're looking at something that kind of looks a little spooky. If you look at it head on, you'll notice that it kind of almost like disappears. But once you turn your eyes to the side and you're looking from the corner of your eye, you'll notice that you can see it in a lot more detail. So keep that in mind whenever you're trying to search for something in the middle of the night. Try to look at things through your peripherals and not focusing directly at them. Um, so here we go. Yeah, this kind of goes on what I was saying before. Um, all right, so corrective lenses. So as you know, I didn't mention this, but uh, because this is a convex, like a convex lens or a converging lens, as we know, light coming through a converging lens will actually create an image that's inverted. So everything that's in front of you is technically inverted on the back of your retina. Our brain, when it takes this information, what it'll do is that it knows that it has to correct that. If you didn't know, our brain does that a lot. Like, for example, our eyes are always seeing our nose, but because it's not important information, our brain pretty much blocks it out. Uh, so that's why anytime you have like something on your nose, it always seems a lot more like out of nowhere. You just see like almost like a floating object there because our brain kind of ignores your nose for the most part, unless there's a change on your nose. There's also things like a lot of sounds that our body naturally hears, but our brain always ignores it because it's not useful for us. It's why if someone is uh, living in a scenario where there's a constant noise being made, after a while your brain just shuts it down because it says, okay, this is always here, let's ignore it. And that's why sometimes it could be more noticeable when you get too quiet because the your brain notices that sounds are no longer being made, and it kind of you end up having like a weird reaction to it. Now there are actually special glasses you can get that will take the images and will actually flip them so that they're right up. Now what this means is that the image when it hits your retina will be upright like it's supposed to. So your brain will at first naturally flip the image, so you'll actually see the um, the entire world around you being flipped upside down. So you'll actually see what it looks like on the back of your retina. It takes a while, but if you wear the glasses consistently, and you make sure that you don't have any peripherals affecting you, your brain will then take that and naturally uh, recorrect itself to no longer flip the image. Like it'll basically train itself, okay, this image is upside down. Every time the hand goes up, I see it going down. So let me flip the image and you know get it right back the right way. So if you're interested, I do recommend trying that out and let me know how it goes. I'm interested to see what someone's reaction would be. I was told that it gets very disorienting. Uh, oh yeah, so this is what I had mentioned before, that we only see the colors from direct line of sight, while corner of the eyes are black and white. All right, so as you know, some people have problems with their eyes. There's three different scenarios. Uh, Nearsightedness or myopia is basically occurs when the object is only able to focus on close objects. So you can only see near things. Typically, what this is caused by is the focal point being a little bit too far away from the cornea, that the retina is a little bit too long. So it says here the cornea is too curved, or the eyeball is too long. So like an image, normally light coming from infinitely far away would strike the back of the retina because that's where the focal point is. But for someone with nearsightedness, it would focus here, and anything far away would end up becoming very blurry because after it passes through this point, it'll end up getting that circle of confusion, that blurriness. So it's only the close objects that will actually be able to focus on the retina. Farsightedness, which is called hyperopia. Yeah. I don't have it, so don't really need to worry about it. This is the reverse. You can only see things that are far away. You can't really focus on things that are close. This is caused by the eyeball being too short or not curved enough. So here's the far-sighted. You know, image from far away will image close would actually focus over here, but when it's far away, you'll end up getting it on the cornea. Um, these are the types of lenses you would get. So if you're nearsighted, you would get what kind of almost looks like a half like plane convex lens. Yeah, I'll call that, or no, plane concave lens. While here you would get almost a convex meniscus type lens. There is a third one called astigmatism, which is where you're just kind of all messed up, like all over the place. No distance is good enough for you. And this is just really caused by your cornea just being all kind of messed up. So, yeah, people with astigmatism are kind of bad at all ranges. This is talking about magnifying lenses. So, uh, the magnification that we get. So this is for an eye focused at infinity. Um, what we end up getting are things like this. Um, the theta is supposed to be uh, about the angle that you would see it from a distance of 25 centimeters. So they say n is being used to define as a normal eye, the length that it would see, and then the angle would be from the top of whatever the object is to the eye. So that's how they find theta, and then theta prime is of the image being created. Yeah. This is what the magnification would end up being for an eye focused at a near point. Telescopes. Um, so you may have known that Galileo did a lot of work with telescopes. A lot of his um, discoveries came from having a telescope. So while he didn't really invent it, he did do a whole lot of special work that led to the heliocentric model of the solar system. It allowed him to see spots on the moon, allowed him to be able to find the planets within the solar system and be able to make accurate judgments, uh, as well as, yeah, just things like that. There are different types of telescopes. There are telescopes that use lenses. So this is a um, what's called a refracting telescope. Um, Basically, what ends up doing is just kind of a gigantic magnifier. Um, the magnification power is found by taking the ratio of the object lens and dividing it by the eyepiece. So objective lens is right here, and then this would be the eyepiece, and you would do that to get whatever the magnification you want. It turns out that you want the objective lens to be very long, and you'd want the eyepiece to be very small in order to get this magnification as big as possible. Uh, you also have telescopes that deal with mirrors and lenses. Pretty much works the same way. Um, each of these types of lenses have different benefits to them. They have pros and cons. Like here, this a lot of times is seen as getting a lot of information, except it does lose a little bit of information of the light that would have come through the middle. Um, so this is another way that you can actually make these eyepieces. So this would be an eyepiece that's directly behind the mirror versus to the side of the mirror. You could have these other ones where you kind of have a converging lens and a diverging lens. So you can read some of these of the different types of telescopes. Compound microscopes work the same way, basically taking a small object, making it bigger. We have a magnification that's very similar to that, to what we worked on before. Again, it has things like the objective lens focal length, the eyepiece. Here you'll notice that um, it's almost a little bit flipped. With the objective lens, the focal length seemed to be a little bit on the smaller end compared to the eyepiece. Um, and then you also have, once again, N for the length that an eye could normally see, and L being the distance between them. Um, this this is something I mentioned before, aberration. So I said before that um, first that light doesn't actually explicitly cross through at the same point. It is a little bit all over the place. So you do get a little bit of spherical aberration just from the lenses not really being super accurate. So you see here you get a little bit of confusion where you would normally get the focal point, but you also do get some of this. So chromatic aberrations, basically the fact that as light is traveling, the different colors of light will actually refract differently. So you'll end up getting things like this where you get the colors kind of almost blurring a bit. Like you'll get the image, but you might end up getting some sort of like color halo around your object. You also get some distortion. All these are caused by lenses because a lot of the things that we're doing are actually ignoring, um, are taking advantage of the small angle approximation. So in summary, these were the equations that we worked on. We did the lens slash mirror equation, the magnification. This was kind of the only thing that we introduced really that was new, was this whole power of lenses. And I briefly mentioned about telescope and microscope magnification. Um, Probably only see like one or two questions on it, and like I said, they'll be plug and chug on the homework. But for the most part, I'm mainly focusing on this stuff. That's what kind of why I skipped the later part. Um, this is the chapter 33 homework. This one's going to be due Friday. So, go through the questions. If you have any questions for me about any of this stuff or anything about the homework, please let me know as soon as possible. And I'll see you in the next one. See you later.